It is the multi-purpose Jekyll and Hyde of the mineral world. It can save you, and it can kill you. It can also conduct electricity, whiten your whites, and ward off the devil. It tastes like no other rock, and just try cooking a decent meal without it. Not gonna happen. We literally can't live without it.
The ceiling's salt, the floor is salt, the walls are salt.
Stand aside, solar and wind. Could salt be the amazing energy source of the future? Now, salt on How Stuff Works. Geologists call it halite. Chemists call it sodium chloride. The rest of us just call it salt. It's in nearly everything, from our blood to this stone, and it has 14,000 known uses. Some refer to salt as the fifth element, as essential to our world as earth, air, fire, and water. But what is salt? While there is a technical chemical definition of salt, what we'll be talking about is the ever-present compound, sodium chloride.
The sodium is a metal, the chloride a halogen, and the ratio is about 40% sodium and 60% chloride. They come together and form an ionic bond. When multiple sodiums and chlorides come together, they form a cube. When multiple cubes come together, they form a crystal, as we're accustomed to seeing in nature.
So, what talents does this little crystal have? Salt is hygroscopic, a fancy word that means it attracts water. Salt dissolves pretty easily in water. Once dissolved, it breaks up into its positively charged sodium ions and its negatively charged chloride ions. That makes it infinitely useful in chemical applications. Salt lowers the freezing temperature of water, making it great for de-icing winter roads. But it also rusts vehicles and bridges in the process. The most obvious use of salt is in our food, where it's both a luxury because it tastes good and a necessity because it's an amazing preservative. What sets salt apart from some other resources is that it's naturally recyclable, so we're never going to run out. If you think about it, the salt on your eggs or on the sidewalk could be millions of years old. So where does salt come from? Salt covers the earth. It's everywhere. It's mixed in with all the ocean water that covers the planet.
Salt crystals develop from evaporating salt water, ocean water, from dried ocean beds. This looks like a dried ocean bed, doesn't it?
Many millions of years ago, after the Earth's surface cooled, centuries of rainfall turned puddles into oceans. The ocean floors were littered with sedimentary rock, which is full of sodium. Meanwhile, chloride spewed from volcanoes and hydrothermal vents. Still, the amount of salt content in these early oceans was likely pretty low. It took billions of years of water runoff, eroding rock, dissolving the salt, and carrying it into the oceans to create the saltiness we know today. Though it varies by location, seawater is roughly 3.5% salt. That translates to about a quarter pound of salt per gallon of seawater, or a total of nearly 50 quadrillion tons of salt in all the Earth's oceans. Okay, so how do we get all that salt out of all that seawater? Harvesting sea salt on a grand scale requires some serious patience. The other key to this process? Location, location, location.
You're located on Great Inagua Island, the most southerly island in the Bahama chain. Great Inagua is approximately 500 miles southeast of Miami, Florida. At Modern Bahamas Limited, we have a unique partnership with nature.
Aside from having access to a limitless supply of salty seawater, this location is ideal for other reasons.
The requirements are high incidence of solar energy, as you can see. We're out here in the sun. A steady but not strong wind, low rainfall, high evaporation, large land area, that is suited for solar salt production.
30,000 acres of Inagua is devoted to the solar salt operation. Each year, hundreds of millions of gallons of seawater are pumped into these primary reservoirs. Shallow basins where the water will sit exposed to wind and the sun's rays. As the water slowly evaporates, the result is a concentrated brine that's drawn into secondary reservoirs and eventually into the final concentration ponds. Each stage becomes a mini ecosystem based on the increasing level of salt.
In our primary reservoirs, millions of microorganisms flow in with the ocean water. Also coming in is millions of fish eggs and other marine animal eggs. These ponds are just teeming with wildlife and a biodiversity of life.
The secondary reservoirs are too salty to support most life, with the exception of algae and brine shrimp. And only salt-loving, aka halophilic red bacteria can survive after prolonged evaporation. The real magic happens in the last phase, crystallization.
It gets to a point where the sodium chloride in that solution cannot be held in solution any longer, so it crystallizes into a solid.
Once the salt layer is about 4 inches thick, the harvesters mechanically scarify or break up the surface and truck it out to the wash plant.
At the wash plant, the salt is dumped into a hopper and it is conveyed on a conveyor belt into spiral classifiers. These are washing tubs where the sediments from the crystallizers, like dirt or sand, is washed out of the product.
The 1 million tons of salt harvested here each year mainly goes toward road de-icing and water softening. All this salt produced with little human intervention. In some parts of the world, salt lakes or oceans evaporated with zero help from us, resulting in salt flats, big exposed beds of salt. Utah's Great Salt Lake is a salt flat in the making, as is the Dead Sea in the Middle East. You can find salt-encrusted seabeds in California's Death Valley and at the Bonneville Salt Flats in Utah. Here, in a salt flat in Bolivia, salt is collected right off the surface, just as people have been doing for thousands of years. Today, salt has many uses, but in the beginning, it was all about food and survival.
We've known about salt's preservative properties ever since the cavemen. And so men have been locating their settlements near salt works.
Salt has been used since antiquity as a preservative. So before there was refrigeration, people salted meat and they salted fish.
Prior to modern geology and industrialization, if you didn't live near the ocean, procuring salt was an arduous proposition. This made salt precious. Trade routes were set up to haul it from mines and coastal regions. Salt was valuable in ancient Rome because it was used to preserve rations on long journeys.
The paycheck of the Roman soldiers was in salt. It was called salario. From this salary, it would be good if we can convince my people over here to be paying salt.
Salt spawned countless superstitions, like warding off bad luck by throwing spilt salt over your left shoulder into the eyes of the devil. And proverbs.
If you read the Gospel of St. Matthew says, quoted Jesus telling his disciples, "You are the salt of the earth," with a double meaning. Basically, having a life with salt, with interest, and also being the savior of the people, of the humanity.
It's impossible to imagine that we could live without salt, and that's why our watchword is salt, the essence of life.
Evaporating seawater is just one of the ways we get our salt fix. A dash here, a pinch there. The salt we eat comprises less than 15% of all the salt produced worldwide. But it's the salt with which we're most familiar. thanks to that unmistakable taste. But why do we eat salt at all?
It's an essential nutrient. An essential nutrient is defined as one that our body doesn't make itself. So if we don't take salt in, we compromise our health.
The body contains about 0.15% salt by mass. So for a 50-kilogram human, about 110 pounds, that works out to 75 grams of salt, or 7 tablespoons.
Salt is an electrolyte that keeps our cells, muscles, and nervous system working. Because when you come right down to it, we run on electricity. Electrolytes act as the electrical conductor that allows our nerve endings to fire, our muscles to move, and our thoughts to form.
Well, the human body is actually a machine. It's an electrical machine, and electrical impulses move into and out of the cells over the cell membranes, and that transmission is facilitated by the sodium.
If that's true, could salt water act as a conductor, connecting two electrodes, lighting this light bulb? Pure water doesn't complete the electrical circuit.
I'm going to add a small amount of household salt. There goes the stir bar, and there is the light. As it goes into solution, the water separates the sodium and the chloride ions, and they allow the electrons to flow from one side to the other, completing the circuit, lighting our light bulb.
All our bodily fluids are salty because salt and water are inherently attracted to each other. But there's a flip side to life-sustaining salt.
Where salt goes, water will follow. And so, if you have too much salt in your body, that can increase your blood pressure. To regulate your blood pressure, if you get rid of salt, you'll also get rid of water.
In other words, too much salt in your body, in your blood, attracts more water than your arteries and veins are used to. Lose the salt and you lower the pressure. How much salt is too much depends on your size, age, and genetics. But health agencies recommend a daily intake of no more than 2,400 milligrams of sodium, or about a teaspoonful. With prepackaged and fast foods flavored with large doses of salt, the average American consumes over 3,300 milligrams per day. But why? What makes salt taste so, well, salty? Salt has that unique flavor because of the sodium ions it contains.
Picture a tongue. If you zoom in very closely into the tongue, you'll find the taste buds. The taste buds are made up of individual cells, and at the tip of each of those cells are receptors to each of the different flavors. For salt, there's a particular channel that only allows sodium through. So when you eat salt, the sodium from the salt goes through the channel, causes a change in the cell, and that change is telegraphed to the brain. Your brain can then detect, oh, I've eaten salt.
According to the famed tongue map, salt is best detected on the tip of the tongue, or so we thought.
In practice, we now know that isn't true, and that you can detect salt all over the tongue.
Salt doesn't just add flavor to food, it preserves it. It even preserves something as potentially dangerous as uncooked pork, which can be full of harmful pathogens. The recipe for making an Italian cured ham, known as prosciutto, hasn't changed in about 2,000 years. It still depends on salt and just 2 other ingredients.
The pork, salt and thyme, and nothing else.
That's T-I-M-E, thyme.
People that work here, they know the meat, they know the salt, and they know the time that it takes to make a prosciutto. We consider them prosciutto Jedi.
If these are the prosciutto Jedi, then this is their master.
Prosciutto actually is the past tense of the verb prosciugare, which in Italian means to dry it out.
And that's just how salt makes raw pork safe to eat, by dehydrating and killing dangerous bacteria.
We apply the wet salt on the skin of the product, just to eliminate some eventual bacteria can grow at the skin level. But the important salt is the dry salt, which penetrates the ham.
Once salted, the hams will age for about a year in different chambers, giving the salt a chance to work its bacteria-killing magic. Each chamber simulates the environmental conditions of a particular season in Italy.
That first stage is, if you will, a replica of what is the winter season. So winter being cold, being humid, at least, of course, in the Mediterranean countries.
The salt works its way into the ham as it draws out moisture and inhibits bacteria activity.
The prosciutto is safe to eat because there is no more active bacteria anyway within the ham. But prosciutto being safe isn't good enough. It also has to be something pleasant. Hence, you have the summer and the fall. And that's really where flavor is further brought out by the salt.
As you traverse this vegetarian nightmare, 100,000 legs of salted hams at various stages of completion hang triumphantly as a testament to time-old tradition. But vegetarians don't despair. Salt can also render vegetables virtually unspoilable. This salt-loving bacteria aids in the fermentation and pickling process.
In the process of going from a cucumber to a pickle, the salt is added to the fermentation brine. It suppresses most microorganisms, but through a selective process allows the lactobacillus organism to grow and flourish throughout the fermentation. The lactobacillus will take the sugars in the cucumber and it will convert it to lactic acid and thus further preserve the pickle.
Once the fermentation begins its active state, we'll start incrementally increasing salt, a little at a time with these shovels.
This carefully controlled salinity in the brine lends the pickles their ultimate flavor, texture, and immortality. So where do we get the table salt that goes in our food? At Morton Salt in Hutchinson, Kansas, salt is mined from underground using water. It's called solution mining. This salt derivation technique exploits salt deposits left over from ancient bodies of water that were cut off from the oceans millions of years ago. These prehistoric salt lakes evaporated, and the residual salt was left on the Earth's surface. Ages of subsequent sediments covered the salt deposits. The weight and pressure of these accumulating sediments compacted the minerals into solid rock layers hundreds of feet below today's ground surface. Solution mining, followed by pan evaporation, primarily yields food-grade salt, a very pure form of salt, the one we eat. Fresh water is injected into deep wells. The water dissolves the dry salt deposits into a saturated brine. More water pushes the brine to the surface.
Brine is brought into a covered evaporator. It's a big teardrop-shaped evaporator that's up to 3 stories tall. And the water in the evaporator is being boiled. And as it's boiled, the steam is rising off the water and it's evaporating, and that's causing the salt brine to condense and form salt crystals. And the salt crystals fall to the bottom of the evaporator, and as they're falling, they're being cleaned.
A heat dryer removes any excess moisture, but this is easier said than done with salt. Because it's hygroscopic, it attracts moisture from the air. So how do they keep the crystals from clumping?
We put free-flowing additives or anti-caking agents in the salt, and those work kind of like a sponge. They absorb the moisture in the salt to help keep it dry and to help keep it from caking.
That additive paves the way for that famous Morton Salt slogan.
Now the salt would flow freely, even in humid weather, so when it rained, it poured.
Salt has a virtually infinite shelf life, both on the shelf and underground. After all, it's just a rock, a really old rock.
Geologists tell us that this salt deposit was formed about 250 million years ago. It was during a time where what is now Kansas actually lay close to the equator, and all of the continents were pushed together into a large supercontinent, which the geologists call Pangaea.
Today, there are several large ancient salt deposits throughout North America. Some geologists estimate that the one under Kansas alone could satisfy America's salt needs for the next 250,000 years. So how do they get the prehistoric salt out from underground? Miners have been chipping away at rock salt here since 1923, using a big boom and some heavy machinery. Okay, maybe it's a bit more complicated than that.
We're going 650 feet underground, and it'll take us approximately a minute and a half. We're going out to the face, to where the mining is actually being done, and that'll take us about 20 minutes.
Down here, salt is a way of life.
Obviously, the environment down here is all salt. The ceiling's salt, the floor is salt, the walls are salt, and to an extent, the air is salt. And you breathe that in, and you can constantly taste the salt. And a lot of the miners, they get to a point where either they go one of two ways. They don't put any salt on their food, or they put way too much salt on their food in order to taste it.
This mine is approximately 2.5 miles north to south and 1.5 miles east to west, and growing every day. The mining method they use here is called room and pillar. This is because large caverns are carved out, leaving behind 40 by 40 foot load-bearing salt pillars. The first order of business, undercutting and drilling 12-foot deep holes.
The reason to undercutter is to relieve the pressure from if you shoot it without cutting it to just stand there. It wouldn't blow out. It'd just be one big glob. What we're doing here, we're going to fill these 29 holes that they just drilled with ammonia nitrate and a diesel fuel mix. It's just a fertilizer. You just take your booster and your Primadet and stick it in the end of the hose. Then you try to hit that hole up there.
Fire the hole!
And 5.5 minutes later, the blast dislodges 300 tons of rock salt.
The salt that we mine today will be used on roads this winter all over the Midwest. Well, on a two-shift day, we take out about 2,000 tons. In a year, we aim at about 500,000 tons, or up to 700,000 tons. We are very dependent on the weather. If there's a lot of ice and snow like last year, we can hardly keep up.
And at about $20 a ton, it takes a lot of salt to pay their salaries. After decades of underground salt mining, there must be something that can be done with all these room and pillar caverns. But what? Deep below the plains of central Kansas lies a company called Underground Vaults and Storage, encased in these prehistoric rock salt walls, hidden away from anyone who doesn't know this place exists. If you're searching for a place to store important stuff, look around. Space is no object.
The available space that's already mined out is over 980 acres. So we will never run out of space, at least in your lifetime or my lifetime.
The current facility uses 1.7 million square feet of storage space and over 6 million boxes stacked on many miles of shelving. And your stuff would be in fine company.
There's just tons of movie film that we store for various film companies throughout the world. We have a complete series of Friends. We see the Dr. Zhivago, that was a favorite, Ocean's 11. And what do you know, here's one of my favorites, The Shining with Jack Nicholson, right back here in the salt mine.
So why is this environment such a good place to store things? Because salt lowers and stabilizes the humidity to a constant 45%. Back up at the surface, Kansas suffers through hot, humid weather for several months of the year. Large fans bring that warm, humid air down from above through the elevator shafts. The warm air mixes with the cool underground air, dropping and stabilizing its temperature. The salt ceilings, pillars, walls, and floors suck up the moisture, lowering the humidity level. The now cooler, drier air circulates around the storage facility to the adjacent underground salt museum, through the salt mine, and ultimately back out to the surface.
We do not have to air condition the facility. We do not have to heat the facility, which saves on utility costs. One of the concerns that we do have underground, of course, is fire. With all the paper and the boxes in the documents we have here, but it's very unlikely because salt will not burn.
Something the Nazis knew when they squirreled away stolen valuables in German salt mines during World War II. The Hutchinson facility was established in 1959 during the Cold War to protect sensitive information and assets.
We have lots and lots of things that we can talk about and other things that we cannot talk about because of the security that we have.
A remarkable example of human ingenuity, partnering with salt to solve the very modern problem of storage space. Salt's properties, harnessed properly, can solve many modern problems. The relationship between salt and water is a complicated one. In the oceans, a delicately balanced, life-sustaining coexistence. In the body, it's more of a codependence. Spreading salt on icy roads becomes a real love-hate situation.
We know that if we salt the roads, we cut accidents by 88% in the first couple of hours after we do that.
Water freezes at 32 degrees Fahrenheit. However, if you add salt, you can depress the freezing point. And this is exceedingly useful because if you live in a cold climate where you have ice and snow, you'll often want to put salt on the ice to keep the streets from being so slippery.
The transition of water from liquid to solid is a kind of chemical reaction. When you throw salt into the equation, the sodium and chloride ions interfere with water's ability to assume the structure of ice. This property of salt, combined with its abundance and low cost, makes it an ideal winter road de-icer. Over 15 million tons of salt get dumped on roads in the U.S. each year. But another characteristic of salt comes into play, and this one's not so beneficial. This is the hate part of salt's love-hate relationship with water. When applied to wet roads, de-icing salt breaks up into its components, sodium and chloride ions. The water layer becomes conducting. Oxygen from the air transports through the conducting water layer to the iron in your car or on a bridge. Oxygen atoms contain 6 outermost shell electrons, a highly unstable configuration, while 8 is stable. As a result, oxygen is always swiping electrons from other atoms, a process known as oxidation. This could spell doom for the metal components of cars and infrastructure.
We are here in Northeast under a bridge that is exhibiting signs of corrosion.
The de-icing salt penetrates the concrete until it makes contact with the rebar structural supports. The salt goes to work, facilitating the oxidation of the metal. The rebar erodes until its load-bearing capability becomes so diminished that the structure is at risk of collapse.
We are going to inspect one of these poles that have been exposed to de-icing salts. We have around 7.5 inches of material that 90% of it has been corroded, perforated. And there is evidence of corrosion products that I'm going to collect for lab analysis. All you need is a bit of force or wind to cause it to have a catastrophic failure.
Back at the Matco lab, Dr. Z and his team do a cause and effect analysis. But just as importantly, they test different materials and coatings in an attempt to curb future salt corrosion.
What we do here in this lab is we test on different metals to see their corrosion resistance. We're going to be putting these into our salt spray chamber. This is what carbon steel looks like after prolonged exposure in our salt spray cabinets.
The salt spray test helps determine how these materials and coatings hold up against a water and salt-laden environment. But it isn't just the snow belt that should be shaking in its winter boots.
Midwest and Northeast and Colorado are areas that they are affected by de-icing salts. East Coast and West Coast both are affected by the salt from the ocean. Now, if you have a situation that you have both de-icing salts and also salt from the ocean, obviously you will have the maximum damage from corrosion.
Still, studies show that the benefits of de-icing salt outweigh the dangers.
We cannot avoid salt because salt is very positive. Salt is very low cost and they are abundant. So in my opinion, they are going to be used for long term. We just have to control the corrosion process. We can never prevent it completely, but we can detect it and slow it down through coating selection and material selection.
With about 70% of U.S. residents digging their way out of snow each winter, when it comes to road salt, we'll take the bad with the good. Americans use up about 16 tons of salt over their lifetimes per person. That's over 400 pounds a year. But don't reach for the blood pressure meds just yet. Sometimes salt is lurking where you least expect it.
The most common use of salt is generally unknown by the public, and that is about 40% of the total salt is used to make chemicals. Like petroleum is the feedstock for the petrochemical industry, salt is the feedstock for the chlor-alkali industry.
Salt is comprised of sodium, which is an alkali, and chloride, which is chlorine. So really, the industry gets its name chlor-alkali from salt itself. Most people think of salt as common table salt, but when mixed with water and electricity is passed through that saltwater solution, you get compounds like chlorine, caustic soda, and hydrogen, which are essential building blocks in everything from food to clean drinking water to pharmaceuticals.
A major manufacturer of these building blocks is this Olin chlor-alkali plant, strategically located near the sources of its main ingredients.
We actually located here in upstate New York, not only due to the abundance of salt, but also because we are near historic Niagara Falls, which makes it a ready resource for low-cost hydropower electricity. We actually receive the salt as a solution from a company about 60 miles away from here. We're really taking advantage of the properties of salt, which is that it's highly soluble in water.
Miles of pipes and wires carry the salt water and electricity to the cell membrane room. Here, electrolysis breaks down the brine into chlorine, sodium hydroxide, and hydrogen, separated by a membrane.
This membrane just looks like a sheet of paper. It's much more than that. It's really a very ion-selective, high-tech polymer technology that allows the sodium ions to pass through the membrane while leaving the chlorine ions on the other side.
Now, what to do with these separated ions?
Every year in the U.S., we produce about 12.7 million tons of chlorine.
Chlorine's molecular outer shell is missing one electron, giving it a unique ability to bind with other elements and compounds. This makes it extremely useful in all kinds of industrial applications.
Chlorine specifically is really known due to its disinfectant properties. It's been used for well over 100 years in the U.S. for providing purified drinking water to millions of people. Well over 85% of agricultural crop protection products use chlorine in their manufacturing process, but it actually has hundreds of other uses and winds up in many other products.
You name it, there's likely some form of chlorine chemistry used to make it. On the other side of the membrane is the caustic soda. As the name implies, it's probably not wise to touch this stuff in its raw state because it can burn.
Caustic soda is another name for sodium hydroxide. It has a number of important uses. It's used as raw material in soaps and detergents. It's also used in the pulp and paper industry to break down the pulp to make paper.
The U.S. industry produces about 13.3 million tons of caustic soda every year, and that equates to about 21 million tons of salt consumed to make those products.
After all that effort went into splitting salt apart, there's something else made at this plant that involves a reunion of sorts. Just add water.
Bleach is produced by combining chlorine and caustic back together, and it's important as a disinfectant in keeping our food safe, in that it disinfects the surfaces that come in contact with our food, not only in our house, but also in restaurants and also in healthcare facilities.
Chlorine bleach kills those nasty microorganisms by attacking them at the cellular level. And it gets those stains out of your whites, but not how you think.
Let's say you spilled some spaghetti sauce on your white shirt. Now the spaghetti sauce is red due to the color in the tomato, the chromophores. And so bleach won't actually clean the clothes. All it simply does is it denatures the chromophore, removing the color, and therefore returning your shirt to white.
The byproduct of electrolyzing salt water, hydrogen, doesn't go to waste either.
Hydrogen is able to displace natural gas in our boilers, and we're not only saving money for the operation of the plant, but we're also helping reduce our carbon footprint and our impact on the environment.
Salt's molecular structure can be harnessed, separated, and altered, proving that it's more than just the sum of its parts. Salt is edible, it makes food safe, and our bodies are full of it. So why can't we drink this? It may be the most ironic way to go, dying of thirst in the middle of the ocean. But the reality is, drinking too much seawater will kill you, and that's because of the salt.
Drinking salt water is a bad idea because your body will try to expel the extra salt by urinating, and it will actually urinate more water than you drank. It has to get that water from somewhere, so it gets it from the rest of your body. It gets it from your circulatory system and from your cells. So drinking salt water actually dehydrates you.
97% of the planet's 326 million trillion gallons of water is in the salty oceans, rendering it undrinkable. More than half of the remaining 3% is tied up elsewhere, so that doesn't leave us with much. Some areas, like Tampa Bay, are looking to desalination as a solution. Through this complex filtration process, you can actually force the salt out of the saltwater. Ironically, the first part of desalination involves a product made from salt.
This is where the raw seawater comes into our plant. This is the first stage of our pretreatment process. And what we do here is we add some chemicals, sodium hypochlorite and ferric chloride. The sodium hypochlorite is common bleach. We're trying to get the particles to settle and collect together, get heavy, and settle to the bottom.
Next, the water is stripped of its minerals and particulates and subjected to reverse osmosis, which removes the salt. In this case, osmosis is the passage of water through a semi-permeable membrane from an area of high salt concentration to an area of low salt concentration. Reverse osmosis uses pressure to push water through the membrane, leaving highly concentrated salt on one side and pure water on the other. It takes about an hour to get from seawater to drinking water. The leftover concentrated brine now contains 6% salt, too salty to discharge back into the bay, so they first dilute it with seawater. Of course, environmental watchdogs patrol any impact on local marine life.
We have an extensive monitoring program. We spend over $1 million a year here at Tampa Bay Water checking for changes in the bay. To date, we have not seen any changes at all.
The desalination process can be pricey. Reverse osmosis requires a lot of energy. And there's another cost to consider when working with salt in a wet environment.
As you know, salt water is very corrosive. At this treatment plant, we had to build the plant with special materials, high-quality stainless steel. That is very expensive, but it will not corrode.
Stainless steel is corrosion resistant because it has a super thin chromium oxide barrier, worth the extra cash. Maybe seawater desalination would be less cost prohibitive if there was a way to produce, say, hydrogen energy in the process. Sound a bit far-fetched? Not to this Erie, Pennsylvania inventor. While researching a way to kill cancer cells using a radio frequency transmitter, he stumbled upon a way to make salt water burn and release hydrogen.
The salt water is just regular sea salt water. This salt water is actually taken from the Gulf of Mexico, so it hasn't been altered in any particular way. We have taken salt water and put Morton salt in it, and it burns the same way.
When a saltwater solution is placed in a specific radio frequency field, the signal breaks the hydrogen-oxygen bond in water molecules, releasing hydrogen and oxygen. Upon recombination through combustion, the hydrogen and oxygen produces the flame. And the byproduct? Distilled water. Could saltwater end the quests for fresh water and alternative energy?
There's no reason why it could not run an engine just the way oil runs an engine. The implications are huge. The purpose of this test was to show that there's energy released inside the test tube, and it expands like gasoline does in a piston inside a vehicle. The gas gets sprayed in, it ignites, and it pushes the piston back. In this particular case, our cork is our piston.
The real-world viability of this is still debated because it takes more energy to generate the radio frequency than releasing hydrogen produces. And the role of the salt is not yet fully understood. But scientists do know that this doesn't work with plain water. They're also testing this process on other substances, though probably none as plentiful as salt water.
If this works, then I think it's a great gift to the world.
Yeah, especially if it lowers those gas prices. While many of our most precious resources are endangered, we can rest assured we're not running out of salt anytime soon.
We naturally recycle most of the salt that we use. We, for example, put salt on the roads to keep the winter roads safe. And that will run off into the streams, into the rivers, and back to the ocean.
My doctor said that salt is bad for me. But I don't trust too much my doctor.
This dinner table staple seasons and preserves not only our food, but our very existence. And who knows, maybe this humble chemical compound found all over the world, with its 14,000 known uses, from seasoning our foods, keeping them safe from bacteria, regulating our water content, de-icing our roads, and even saving our beloved movies, actually has 14,001.